Hello, my name is Frank McKenna. I work here at UC Berkeley for the NHERI SimCenter, which is a National Science Foundation funded project. This is part one of a three-part series on how to use the SimCenter EEQ application. Now, before we start part one, this is a brief look at what we will be covering in each of the three different parts. In this part, I'm going to give you a brief introduction to the tool itself. In the second part, we will be covering earthquake events and how to submit a job to a high-performance computer. And then lastly, we're going to be looking at site response, and in particular the SHARC application. Now in this part, today I'm going to be giving an overview of SimCenter. I'll quickly describe the research and educational applications available from SimCenter, and then we're going to spend the majority of the presentation in the introduction to the tool itself. Let me start with a brief overview of the SimCenter, just to give a context for the applications we are providing to the community. The Center is led by co-directors, Professors Gavinji, who is the project PI, and Professor Dearline. The co-PIs in the project are Professors Kareem, Lowe's, and Rao. The SimCenter Associate Director is Matt Schuttler, and I look after the software development. My software development team includes myself and a number of postdocs and faculty members. This isn't about the features and applications and algorithms to include in the software. These are guided by input from our list of domain experts, of which there are many. Now, where does SimCenter fit within the NHERI organization? We consider ourselves to be a virtual experimental facility producing software. That software exists on DesignSafe and runs on DesignSafe. The software is intended for researchers both within NHERI and, more importantly, researchers outside NHERI and practicing engineers, all working in the field of natural hazards. Our mission is to transform the nation's ability to understand and mitigate the effects of natural hazards through advanced computational simulation. We like to say it's grounded in the present, it has a 5-year focus, but has a 20-year vision. So what software is needed to effect the transformation? Grand Challenge reports published over the last 3 decades all identify certain needs, research needs, to address the challenges. In particular for software, the reports all identify somewhat similar needs. One is that the applications are needed that produce uncertainty quantification measures in the response. Second is that performance-based engineering applications are needed for hazards other than earthquakes. The third was we need to go beyond looking at the response of single buildings. We need to look at the impact of hazards have at the regional scale. And finally, tools are needed to educate our students and engineers. Now, the SimCenter has taken these requirements and are releasing applications that begin to incorporate these needs. More specific requirements as to what these applications should do in the future, these suggestions need to come from yourselves. We provide an online forum as a means to send us feature requests. Here's an example, for the QuoFem forum where users are submitting feature requests. Our goal is to produce software that researchers in the natural hazard engineering field can use in their research. To do this, we're building an open source framework that will allow us to build applications, specifically scientific workflow systems that include EQ in the response. We're designing the framework to be flexible, extensible, and scalable so that different components can be enhanced and improved by members of the community. We're seeding this framework with enough components so that it can be employed in the near term, and using the framework, we're building and releasing applications that engineers can use now in their research. Finally, through our applications and our community forum, we're hoping to build an ecosystem that fosters collaboration between researchers. So what is a scientific workflow system? A scientific workflow system is an application that allows users to build, launch, and monitor scientific workflows. So what's a scientific workflow? A scientific workflow is an automated workflow of applications in which multiple applications are invoked following a workflow description, with data passed automatically between applications in the workflow. Let me demonstrate with a simple jigsaw analogy. So of the jigsaw, each puzzle piece represents an application, and the workflow management system moves the data between one application to the next as one application finishes and the next starts. The scientific workflow system allows the user to specify which applications go into each jigsaw piece. Now we're trying to incorporate as much existing software as possible. To do that, we're writing pre and post processors to existing software. And we're also wishing to use the data and HPC resources that DesignSafe provides. So these features are all being incorporated into our software. This is the current design of the SimCenter framework. Down here in the light gray, I'm showing the different components of our framework. Above that, in the white area, we're showing the applications that are built using the different components. The lines are indicating which components go into the different applications. And as you see, some of the applications are built using some of the existing applications. They build upon each other. Down at the bottom, I'm showing the external applications and libraries. These are the applications for which we've developed pre and post processors. Now the SimCenter, of course, is not running deterministic workflows, i.e. you do not get a single number for each response quantity. Instead, the workflows are UQ workflows. For each response quantity, they will generate a measure of the uncertainty in the computed response. Now because we're doing UQ workflows, this requires extra input from the user. The user has to identify certain parameters as being random variables, and then they have to assign distribution to those random variables. Now, in addition to requiring extra inputs, the UQ workflows also require extra computation. The SimCenter application is solved by running either using all the CPUs on your local machine, or they allow you to run the computations at the HP resources provided by DesignSafe. To do this, we've had to split the applications into two. We have the front-end user interface, and then the back-end workflow management system that actually runs the workflow. So the front end is just your typical desktop application which you interact with. It's the front end that launches the back end workflow. It provides it with an input file. The back end workflow management system reads the input file, figures out what the workflow is, launches the workflow, and then when it's done, it returns control to the user interface. And I'll go over this in detail later when we get into the application itself. So now let's get into showing you what research applications SimCenter has produced. There are 4 applications that are available for download now. The first of these, QuoFem, integrates finite element applications with uncertainty quantification engines. These are UQ applications. The existing finite element applications we're looking at are shown here: OpenSees PV and OpenSees Pi. The UQ methods these applications now are imbued with are sampling, sensitivity, reliability, parameter estimation, and Bayesian calibration. Our second application, EEQ, quantifies the uncertainty in the building response when that building is subjected to an earthquake. The inputs are building information. There are various structural modeling capabilities the user gets to choose from and different ways to apply the earthquake event. And finally, of course, we bring in the forward methods, the sampling methods, and the reliability methods from QuoFem. The third application, WeUQ, right here we're looking to quantify the response of the building. Now when the building is subjected to a wind event, the wind loadings we're looking at are CFD simulations, wind tunnel events, and stochastic loading events. Finally, the PBE application. This is an application for determining the damage and loss when the building is subjected to a natural hazard. Again, it's building on top of EEUQ and WeUQ, bringing in all the different structural modeling and loading events. Currently, it's limited to earthquakes. We're hoping this year to get in the wind event loading so we can do performance-based wind engineering. Here's a tool that actually hasn't been released yet. It's RDT. It is coming. This is our tool for doing regional damage and loss estimation when the buildings in a region are subjected to a natural hazard such as an earthquake or a hurricane, where we're looking at hurricane winds and storm surge effects. Now let's briefly look at the SimCenter educational software. We have released 4 applications. MDOF and EVW are applicable to courses in structural dynamics. PGT, a pile group tool, suitable to a course in geotechnics. And finally, BFM, an application that allows users to model brace frame and compare with experimental results, suitable to steel design courses. Now, in addition to the educational applications we release, some other educational activities of note within SimCenter, we do try and hold in-person training events showing people how to use our tools. We try and hold 2 of these a year. We do have a summer programming bootcamp, which is an intensive week-long event in which we show students how to program, how to write parallel code, and how to write applications similar to our own which interact with DesignSafe and interact with the World Wide Web. And then finally, we have an undergraduate REU program where we invite undergraduates to come to UC Berkeley to work with our postdocs for the summer. So now we get to the heart of this presentation in which we introduce you to the application itself. I'm going to break this into three. We're going to do a tool walkthrough. I'm going to show you what happens when the tool is actually running, and then we're going to go through the various options. In each of these stages, I'm going to do a demo with the tool itself. So first, the tool walkthrough. Why do we want uncertainty quantification in earthquake engineering? Here's two rather famous quotes. I kind of like the second one. The uncertainty is as important a part of the result as the estimate itself. An estimate without a standard error is practically meaningless. If that is not a motivation for why you should want uncertainty quantification measures in your response, I do not know what is. The tool itself, we're currently at version 2.1. We have a number of various loading options, uncertainty quantification methods, and model generators. Year 4 updates we're trying to get into for version 3 are shown here. The one in red, reliability and sensitivity, that is actually in version 2.1. So in the user interface, what are the applications you get to select from? Which applications go into the different jigsaw pieces? For the UQ and FEM applications, there's only one option available to you. For both the SIM and EDP, we have two options available. And for the event itself, we have a number of options. And these are the focus of the next two part of this series, and we're not going to get into them today. So now I'm going to do a quick demo of the tool. I'm going to quickly show you what the interface are by selecting different buttons and just showing you the general usage of the tool. I'm going to demonstrate the tool with an example taken from Professor Chopra's Dynamics of Structures book. It's problem 12.7. I'm going to also show you how to load and save your files, how you can get to the documentation and the message board straight from the tool, and then for the results, when you want to see the results graphically, what left clicking and right clicking of the mouse will do. So now let us go to the tool itself. So this is what the tool looks like when it starts up. On the left hand side we have this selection bar. By clicking on any of these items we bring up those different jigsaw pieces. In each jigsaw piece, which application we want to use. That is done at the top of the thing. There's going to be a pull down menu with the option to pick whichever application you want. I'm going to stick with stochastic ground motions here. At the bottom of the tool we have a number of buttons. We have 4 buttons. The first button is to run the tool locally. The next 2 buttons are for working with DesignSafe. The first button runs the job at DesignSafe, and then the second will to get the results from DesignSafe. We'll show that a bit in more detail tomorrow. The exit button, of course, will close the tool. When you're working with DesignSafe, this button, top right, this login button, that's the button you press to log in. When you press it, it's going to bring up a form where you enter your username and password. So to use this at DesignSafe, you are going to have to register at DesignSafe to use those HPC resources. Now this area here in the tool, this central top part of the main window, that's where you'll see error messages and status messages as the tool is running to show you what's going on. And there are, of course, the file and help options. Let me just go to the help options now while I'm here. If you select help and you go to the manual, it will open up a web browser and take you straight to the online documentation. I will close that. Go back to my application. If I now go to submit a bug or feature request, again it's going to open up your web browser and take you to the form for EEUQ. Let's go back to the tool, close Chrome here. So now next step is let's go through that example 12.7 in Professor Chopra's book. So for the UQ, I'm going to do forward propagation. I'm going to stick with Latin hypercube sampling. I'm going to change the default number of samples to something still small. Let's do 100. Still a rather small number. General information tab, we're going to leave that alone. Sim, we're going to stick with the MDOF, which is our shear building model. For the number of stories, we're going to specify 3. It was a 3-story model. We're going to use a W for the floor weights, we're going to create a random variable, give it the name W. When I enter W here, you see the weights in all the different floors are now given also W. Story stiffness, we're going to use a random variable K. Again, K for stiffness in both directions. The weight of the roof was slightly different. So here we will enter WR, just the weight of the roof. Okay, so here we have our 3-story model, 3 random variables, W for the weight of the floors, K for the stiffness, and WR for the roof. So let's go to the event. For the event, we're just going to go back to the stochastic ground motion. Use the default seed. We're not going to change the magnitude or anything like that. Just leave everything else alone. For the finite element analysis engine, we're sticking with OpenSees. It's our only option. And these are the analysis options for the transient analysis. We're going to keep the defaults. EDP, again, we're just going to stick with the default. Random variables, here we are going to enter the distributions for those 3 random variables we created. By default, they're normal. We do have other options, which we can see with the pull-down menu. W was 100. Standard deviation will say 10% COV. K is, let's just say 325. For the standard deviation, we will give it, say, a 50 kips per inch standard deviation. Weight of the roof, 50 kips. Standard deviation 5, which again is a 10% COV. Now if we wanted to quickly see what that looks like for the PDF for that, there's the PDF for those values that we entered. As you see, it's got a mean 50, and that's what a standard deviation of 5 looks like for that distribution. So now to get to the results, if we click on results, we'll have nothing. To get results, we need to click the run button. So we're going to specify to run it locally. So this will take a little bit. This is an 8-core machine. I'm using all the 8 cores, but I'm doing 100 dynamic analysis. It'll take a few seconds longer probably. And when it's done, it will bring us to the results tab, where we will see the mean and standard deviation for all the response quantities. Here we are. For all our different response quantities, here's our mean standard deviation. We also see the skewness. Is it skewed left or right about the mean, the data? And also the kurtosis, what does it look like compared to a normal distribution? Is it skinnier or fatter? If we click on the data values tab here, we can graphically see all the results, and for each of our 100 runs, we can see the WK and the WR, what the values were for our random variables, and then what the values are for each of our response quantities. By left-clicking on a number here, one of the numbers, we will bring that column as our y-axis here. So I left-clicked on the one PDF31, so that was the floor displacements at the 3rd floor in the 1 degree of freedom direction, and my y-axis is now this. If I want to change my x-axis, for example, if I wanted to look at how that displacement is changing with, say, the stiffness, if I right-click in a number in this K column, my x-axis now becomes K, and we see there is a tendency as we increase K, we get a decrease in the displacement. Now if I right-click and left-click in the same column, you see now I've only got one column highlighted. The last thing I did was a right-click. I get the CDF for that response quantity. If I left-click, I will see the PDF for the response quantity. Again, let's see, I gave a normal for K. Let's see if we got a normal. So we will left-click, and then we will right-click, and there's the CDF. If I left-click again, I will get the PDF, and we see there's our normal distribution that we entered. And we see that because we're using Latin Hypercube. If I had run Monte Carlo with that few samples, I might not have seen that. So now we get a file save. Let me just save that as, we'll save that file. We'll call it P112/7, just if we need to come back to it. We'll save it in my home directory. Click the save. Okay, so that's done. So we will exit the application now, and we will go back to my presentation. So let's look now and see what happens when we actually run a workflow. We want to look at what's actually happening to the file system. This is quite instructive if you need to debug your application, find out why it's not running, why the results are not showing up. So the application itself, remember it's split into two. We have our user front end and our workflow management system. When you click run with the front end, it's turned over to the back-end system. The back-end system is going to run a UQ engine that is going to run a number of deterministic runs. Each of these deterministic runs, it's going to pass to a workflow driver, the parameters it wants to use for that deterministic run, and then the workflow driver, when it's done, is going to create the results.out. The workflow driver itself is a file that is actually going to run the different applications. Now this, of course, is done in your file system, so what actually happens when the run button is pressed, the first thing the application does is it's going to read a workflow applications.json file, which associates the application with the application you specify in the user interface with an actual compiled application that's sitting on your system. It will then create a folder. That folder is in your documents EEUQ local runder temp.simcenter. It's going to into that directory is going to place a file dakota.json. That is the input file for our workflow management system. Once that file has been created, the user interface is then going to launch this workflow management system, which just happens to be this application femuq.py with that input file as the input argument. That system is going to create the workflow driver file and also an input file for the Dakota application. That's the UQ engine. Once these files have been created, it's actually then going to launch Dakota application, which is going to repeatedly do that params, call the workflow driver, get the results.out. When it's finished, Dakota will write two files, dakota.out and dakota.tab.out. These are the results files. It will then notify the workflow management system that it's done. The workflow management system will notify the user interface that it's done, and the user interface just reads in the two output files created, in this case, by Dakota. And all these files exist in this folder temp.simcenter, which is in your documents directory. Let's do another demonstration just to show you all those files and that they are created and where they are. So we'll repeat the last example. The only difference is this time we use the ground motion in the examples directory, the lcentro.at2 pure ground motion. So let me go back to the application. Let's start it here. There's my application. Just resize it a second here. Size the window. Okay, there's it resized. So let me, I guess the quickest way to do this, let's just open up that file we just saved. It was in my home directory, p127.json. Okay, so I've opened up that file. The event we had, let's just, there's a three-story building with our WK and WR. So now, instead of the stochastic ground motion, we are going to select multiple peer ground motions. We're going to add that ground motion, which I have on my desktop. EEUQ examples, peer motions, there's lcentro.at2. We're going to load that up. We'll just give it a name, lcentro. So now we put the name there. So there's the lcentro ground motion. If I wanted to put a scale factor, if I want to put a random variable here, I could. Why didn't I? I wasn't intending to, but let's just do that. So now we've got lcentro ground motion that's acting in the 1 degree of freedom direction, and we've got a random variable factor. FVM, we're going to leave alone. Actually, no, we're not. Let's do a little bit of something different here. So let's specify we're going to have tangent stiffness damping. Rayleigh damping, so that needs 2 modes for Rayleigh damping. So we'll do 1 and 5, actually 1 and 6. The model creates 2 degrees of freedom at every floor, so that's 6 degrees of freedom. So to get the first and third for the planar problem, we want to specify 6 modes. So we'll actually specify 5. 5 will work. Engineering demand parameters, we have this new random variable factor. Let's give it, well, let's do something different. Let's give it a uniform distribution between, say, 0.9 for the minimum and 1.1 for the maximum. I'm going to cut down the number of samples. This is not, let's just run this quick. We'll just do 20 samples this time. Don't want to look at the results. We want to look at something else. We want to look at the file system. So this should run a lot faster. There we go. So I'm going to exit the program again. Now we're going to look in this. So if I'm going to go to the documents folder, /documents /EUQ, if I cd here, so let me show you what I've got. I got local workdir, remote workdir, and a debug.log. Debug.log contains, as the program runs, we output messages. These go to this debug.log in case we need to help you track down what the problem was. Each time you run the application, it starts a new debug.log. So we're going to go to cd local workdir. Here, we're going to go into temp.simcenter. These were created by the application. We ran this one. We did 20 samples, so there we have 20 workdirs. We have this templater. This is where all the files are put by the UI. One of these files is dakota.json. So if we just look at this quickly, cat dakota.json. So at the top of this file, it will show the different applications we picked for our jigsaw piece. We're using the standard earthquake, existing peer events, multi-degree of building model, OpenSees. Dakota was our UQ engine. EDPs were standard earthquake EDP. And then for each option, it'll specify, there's our peer ground motion, that shows which the file was, and also shows that for the factor, we created a random variable whose name was factor. This is the general information. The simulation was this OpenSees. There are all the analysis options. This is structural information. This is our MDOF model. We have for each floor, we're going to have values. Well, for the UQ method, the Latin hypercube 20, the seed was 53. What else? Then for the random variables, we see what it was normal. Each one will have its, what its distribution type was, and then the particular properties for that type. So that was a dakota.json file. In here, our workflow management system, it also creates this workflow driver. On a Mac or Linux, it will be workflow driver. On a Windows machine, it will be workflow driver.bat. If we just look at it, basically it's basically invoking all the different applications, and this first thing it's doing is it's taking the params file and putting into the file that the applications expect what the actual values are. So that's the templater file. One directory up, we're going to have, if we ls it, we'll have a file dakota.in. This is that Dakota input file that got created. If we look at this file, it will show you our response descriptors. What else will it show? So show the random variables and what their values were. Latin hypercube, 20 samples, and we want to save the results in Dakota tab.out. So that's the files. Now let's go back to our presentation again. So now the last part of the presentation, we're going to slowly go through the different options that are available. So let's start off with the SIM, this structural information model. This is the application that generates the structural analysis model that the finite element application will run. There are two. There's MDOF, which we've been seeing to date, and there's also this one called OpenSees, where you can specify as any OpenSees model. MDOF you've seen. Something I didn't mention when I was going through the tool is we have these eccentricities. For the mass eccentricity, the mass does not need to be centered where the center of, say, structural resistance is. Also, we can have that the response quantities, we want at the corner of the building if we've got torsion going on. We don't want it at the center of stiffness, so we would specify an eccentricity for the response as well. Everything in this form can be a random variable except the number of story heights, and the response eccentricities. OpenSees model, for those of you who knows OpenSees, this is what the interface would pop up with. You specify in your input script what the main OpenSees script is. You also have to tell it what the nodes are at the different floor levels for which it will record the information. You specify the spatial dimension of the problem and the number of degrees of freedom at a node. Now in the OpenSees script, this main script, none of the other scripts, you can have this pset command. Pset is similar to set, it just identifies it as a parameter. And once inside this tool, the program will open this file, look for any psets, and automatically create random variables with these names for you. Options for EDPs. The standard earthquake one is the one we've been looking at. There's also a user-defined option where we don't want all those different response quantities. We want to create our own. For example, we might want story shears. That's not in the standard earthquake one. So again, here's the standard earthquake. We get all this output for each floor. We get the peak floor acceleration. Now that's total floor acceleration, where we will add the ground acceleration to the relative acceleration to give you a total acceleration. For a user-defined one, this is what the form would look like. You specify two additional scripts. One contains the recorder commands in OpenSees. For example, shown here, where we're using an element recorder for the forces at each element, and we're using a node recorder for the nodes 1, 2, 3, 4 in the 1, 2 displacement directions. The second file is a post-processing script that will read these node.out or forces.out files and produce the results.out file that Dakota expects. Now, once you're using a user-defined one, you have to give names to the response quantities. The names cannot begin with a numeral. They have to begin with a letter. And there's no spaces allowed. If you want to try and give a space, you can put an underscore or a minus sign, but no spaces between the variable names. Here's two examples of post-processing scripts. As I mentioned, they can be either a Tcl script or a Python script. Python, it might be more useful if you're creating a lot of numbers in your output files. The Tcl one is pretty easy for just opening files that have very limited data. There's not much number crunching involved. So the two things we're going to do, we're going to open node.out. We're going to create a results.out file, and into results.out we're going to put our results. Now the one thing when you run a Tcl script is that the program will automatically create a list named listqoi that you can use in your post-process script. When you're using postprocess.py, again, we're going to open node.out. We're going to read all the data. We're going to write the data to a file results.out. So somewhere here I'm going to open up results.out. So there's results.out. I'm opening up results.out. And the arguments that, like q of I for each of the response quantities, they're coming in as system arguments to a Python script. As you see, you can then we can greatly reduce the output to what the response quantities we're interested in. For the FEM, there's only one option, OpenSees, and here you're specifying the analysis options for the OpenSees analysis script when it's running the dynamic analysis. You do have the option to provide your own analysis script, because not all nonlinear analysis converges, and here is an example of where we do not want to use the defaults. We want to use our own OpenSees analysis script to perform the analysis. So I thought I'd go back to a demo now. I'm going to use the stick model that's in the examples folder, and I'm going to use the analysis script as well, and I'm going to use user-defined EDP just to show you how it all works. So let me go back now to the tool and do this. So here our tool is started back up. We said we do 100 samples. We wanted to do a sim model. We want to do an OpenSees model. That model was in our desktop applic folder, EEUQ examples, OpenSees shear building model, and we're going to use the stick model. Later on with the exercise, I'm going to ask you to look at this frame model here. So for right now, I'm going to use the stick model. I'm going to specify open that. The nodes at the different floors at which we were going to look at the response are going to be nodes 1, 2, 3, and 4. And they're comma separated, or they could be space separated values. For the event, we said we'd do El Centro, so that's in the multiple peer again. We're going to add an event. We're going to choose. That is one directory up, and it's in the peer motions, and it's El Centro. Here's El Centro. I'll finish up giving it that name. It's acting in the 1 degree of freedom direction, and it's the scale factor 1, so I'm going to leave that alone. Get to the FEM options. Here, instead of Rayleigh damping, I'm going to use modal damping. I'm going to specify 2% in the first 3 modes, and we're going to have 0 to stiffness proportional damping. For the EDP, for now, I'm just going to use standard earthquake. I'm going to fill in my random variables, normals. We're going to give them all normal distributions again. Weight, it's got 100 kips, 10 standard deviation. Weight of the roof was 50 kips and a 5 standard deviation, and stiffness 325 kips per inch. Let's say 50 on our standard deviation. Okay, we've got everything set up. So we can now run this. So here are the results. The roof displacement is this 1.38, second floor displacement 1.2, and the first floor displacement 1.1. So let's go back and change our EDPs from using standard earthquake. Now we're going to use the user-defined option, the input file that we're going to add to get the response quantities. We're going to go back to the examples. In that open shear building model, I have this recorder commands. I'm going to use those recorder commands. For the processing script, we're going to use postprocess.tickle. There's also postprocess.py. If you want to play with that one later, you can. So now I've added my 2 scripts, but I still have no response quantities. I have to say what my response quantities of interest are. So let's just say node 4, disp 1. So we're looking at node 4 displacements in the 1 degree of freedom direction. Node 3, disp 1, and node 2, disp 1. Okay, so there's my 3 quantity of interest now. So that's all I've changed. Everything else is the same. I just want to use the user-defined output. So I'm going to run this. Take a few seconds again, and when it's done, I should just see 3 response values, and there we have it. And there's those 1.37, 1.2, and 0.72 again. So now let's do something else. Let's go back to the finite element thing, and instead of using the default options, let's use the commands that are in that analysis script. So the analysis commands.tickle. I'm going to specify that, and I'm going to run that. So I'm now running with the commands in here as opposed to the defaults up here. So here are the values, and they're looking the same as before we added the analysis commands, just to show you that we should get the same results if we're doing the same thing. But again, nonlinear analysis don't always work, and you do need that option sometimes to be able to specify your own analysis commands. So with that, I'm going to keep this up. I'm going to go back to the presentation. So let us continue and now look at the options available within the UQ panel. There are three types of method available. We have Ford problem, better known as sampling, sensitivity, and reliability analysis options available. For the Ford problem, we've seen these. We're taking the distribution on our random variables. We have our workflow, and we run a number of simulations, and then once we're done, the results show you the mean, standard deviation, kurtosis, skewness. You can look at the CDF and PDFs. For each quantity of interest, you can do that. We've been using Latin hypercube sampling up until now. Other options available are Monte Carlo and importance sampling. For those cases where the workflow takes an awful long time to compute for each deterministic simulation, there are two surrogate methods available: polynomial chaos and Gaussian process regression. Sensitivity, we do pretty much the same thing. We're inputting our distribution on the random variables. We're going to run a number of deterministic simulations, but the output, we're just showing you the Sobel indices for each quantity of interest in respect to the different random variables. And there are two options available here: Monte Carlo and Latin hypercube sampling. And what sensitivity does is trying to figure out how sensitive the quantity of interest are to each of the different random variables, and that is what the Sobel indices measure. Lastly, we have reliability analysis. It is slightly different. Again, we define the random variable distributions, and also when we're defining our method, we define for a single quantity of interest the values at which we would like to know the probability. For example, if we specify two values, we're going to get the probability on the CDF corresponding to these 2 points here on the CDF, and we'll see that in the demonstration. The methods available, we have local methods and also global method. The global method really is the best for highly nonlinear problems. Again, it works only for problems with one EDP value. You cannot use the standard earthquake here. You have to use the user-defined, and you only can specify one response quantity. That's a limitation of Dakota. The different distributions in normal, beta, Weibull, log normal, uniform, and Gumbel. This slide here just shows you what the different distributions like with different input parameters. So let us now go back to the demo. In this case, I'm really demonstrating sampling, sensitivity, and reliability methods. So here we are back at the tool. This is where we left it. We got results for our random variable. These were our distributions. These were the EDPs. Remember, we're using user-defined, looking at the node 4, node 3, and node 2 displacements in the 1 degree of freedom direction. We were using OpenSees with our own analysis script. The event was El Centro. The simulation model was this stick model inside that directory. And finally, we were looking at the forward propagation problem with Latin hypercube. As mentioned in the previous presentation, we had a number of other options available for forward propagation. So before I do anything, let me quickly look at the results. I need to jot down some values. So I'm going to switch on to the data values. Node 4 displacement, what does the CDF look like? It's not that smooth. So when we get to the sensitivity, when we get to the reliability, we're going to specify 1.4 and 1.7, and we should see about around 70 and 80, 85. So 1.4 and 1.7. All right. So now before I forget those numbers, let's slip to the reliability analysis. So I'm going to use a global reliability. My response levels was 1.4 and 1.7. So there we have it. Let me hit run. And this will take a little while. And here you see expected one function values, but 3 found. This was our EDPs. Remember I said the reliability can only take one quantity of interest. There's a little error you're going to get if you try and do what I just did. So now we'll do it for 1. This will take a few seconds. So here we go. We get our response for our 1 point values 1.4 and 1.7. These were our 2 levels we specified, and we see we get about the 70 and the 85% that we saw previously. So let us go back now. Our last method, we're going to use a sensitivity analysis, Latin hypercube. We will specify more than 20, but not too much more. This will actually do a lot more samples than you specify, trying to figure out how sensitive these parameters are. For the EDPs, let me go back. We can add again more response quantities. Let's just node 3 disp 1 and node 2 disp 1. Remember, in sensitivity, we're trying to find out how sensitive the responses are to the random variables. And to demonstrate this clearly, I'm going to add a dummy variable that should have no impact on the results whatsoever. I will give it a mean of 325 and a standard deviation of 50. So I'm now adding a random variable that should have no effect on the responses. So we should see our Sobel indices of 0 for these dummy random variables. So let's run that and just to confirm. And then we'll see how sensitive the results are to the other ones as well. So again, this will take a little bit longer than the forward sampling, just because it's going to actually run more than those 50 samples. So there we are. So as you see, the Sobel indices for the dummy for all 3 risk quantities are basically 0, saying that the dummy random variable has 0 effect on the responses. And then for the others, we see the Sobel indices, K has the largest impact on the quantity of interest. The W's are smaller. So with that, I will go back to my presentation and bring up some exercises. There's 2 exercises. I'd like you to repeat that last exercise I just did, but for the shear building, using that frame model that was in the directory that I pointed out when I was going through the demo, and pretty much do exactly the same thing I did. And then I'd like you to repeat the whole exercise again for a different model. You can use the MDOF or you can use OpenSees. The example is problem 13.2, again in Professor Chopra's Dynamics of Structures. And if you can get through these 2 exercises, you should feel pretty comfortable that you're able to understand and work the EUQ. Again, tomorrow we will look in more detail at the earthquake events, and then the following day we look at the site response tool. Thank you for your attention.